Welcome to a lesson with Dr. Powell. Let's expand on the last example where we were talking about area and finding the derivative of an area function is simply the y value of the curve itself. Well, what if we think about a volume like a cone? So it's the center of the cone, and let's suppose we have a line through it that goes like this, and we're taking different x values. Maybe this is an x value of 0, and it just kind of goes along this way. And then for each different x value, we can kind of think of a volume function as being the volume between this shape, or the outer shell of this shape of this cone, and this axis itself. So basically just the volume starting at this point all the way up until x. And so this right here would be like the volume up until this point x, just like we have the area under a curve, but instead we're going to have the area between a surface and an axis. So kind of everything that fills in the area up to this point. So we can think of the volume up to this point, and maybe if we go a little bit further, we can take the volume to that point. Now, this type of situation actually happens like in when we have water in a cylindrical tank. Actually, the observation we're going to make now is going to make the rates problems with cones a whole lot simpler, and we'll illustrate that in another video. But here's the starting of the idea, at least. Right here, this little piece, let's think about this. What's the derivative of this volume function? The volume in the cone starting from this point going till there. Well, let's take the change of volume. So if we go to volume to there, then the volume to there, the little change of volume is going to be the volume of this little piece of this section, which I've redrawn over here. And I'm using this notation here. A of x I'm considering to be the area of the cross section that I'm going to. So from here up until the x value, so the area of the cross section that's made if you slice the volume right there at that x value, that's A of x. So if I go a little bit further on the other side of the change of the volume function, it's going to be I'm going to take the area and I'm going to label it as area of x plus h. Now, so this right here is a little picture of the change of volume. Change of volume could be thought of as v of x plus h minus v of x. So the volume to this point minus the volume to that point gets you the volume of this little section. Now this change of volume is actually situated between two different volumes. Now, namely, this guy is bigger, this cross-sectional area. What if I were to take this cross-sectional area and just multiply it by h? That'd be like taking the area of right here, the area of a cylinder where it's base times height. The height would be like h, going this way in this direction, and the base would be right here, which would be A of x. So the A of x would be the area of the base times h. So that would be this volume, which of course is going to be, so think about going out this way. So, going out here, we're getting a bigger cylinder here to go around. And that is going to be bigger than my change of volume. Now, if I take this one, it would be smaller. I get a cylinder that would be smaller. If I just kind of went inward like this, I get a volume that's smaller than the actual. So, and so I get the change of volume sandwiched between these two guys. What if I take the change of volume, which I can rewrite like this, and divide everything by h? Then I get this inequality. And as limit as h goes to 0, I get this sandwich, which means that the derivative of the volume is nothing more than the area itself of this cross section as I go along here. So as I increase my volume going this way, the derivative is precisely the measure of the forefront of the growth. Measure of forefront of growth that's perpendicular to my growth is going to be the derivative, which is just an area. So kind of the surface of the growth is the area and of that cross-sectional piece. So that means that I can actually compute what the derivative of volume is by just cutting a slice right here and looking at the area of that cross-section piece. Now this works, these limits work, meaning that we can actually pass the limit inside of this a function, assuming that the area of the cross section is continuous. That comes from being the boundaries of these kind of being continuous type shapes or curves or continuous surface, if you will. If you're finding volume and continuous surfaces, you always can do this in this particular manner. Thanks for watching.